Okay, so it gives me great pleasure to introduce today's speaker, who is Alexandre Guillaume from NASA Jet Propulsion Lab in Pasadena, California. Do you want to go ahead and share your slides, please, Alex?
Certainly. And let me know if this works. Can you see my screen? Oh, not yet.
Yeah, here it comes. Here it comes. And then maybe, yeah, that's looking good. Okay, so Alex is going to talk to us about stochastic parameterization of an atmospheric model assisted by quantum annealing. So over to you, Alex.
Well, thank you very much, Paul, and good morning and maybe good evening to all of you, depending on where you are. So I'm Alex Guillaume, and the work I'm going to talk about today was done with me, Youngmin Seo, Marcin Kurowski, and William Khouider. And when I met Paul early June, it was at the Adiabatic Quantum Conference in Glasgow. And there I saw some talks on theory, algorithms, and experiments, different physical implementation of adiabatic quantum computing. Today, it will be a presentation just of an application given a commercially available quantum annealer. So there's quite a few slides of introduction. I work at the Jet Propulsion Laboratory where I'm interested in applications. And one of them that's important to me is climate. So this first slide introduced two of the concepts. First is weather. And weather is the fluctuating state of the atmosphere around us, characterized by the temperature, wind, precipitation, cloud, and other weather elements. And the key point is the limited predictability of it. Beyond a week or two, individual weather systems are unpredictable. And climate definition is based on weather. In a narrow sense, climate is usually defined as the average weather over a period of time ranging from months to thousands or millions of years. So I thought I would indicate different sources of information because it's an important topic, going from a worldwide organization, which is the Intergovernmental Panel on Climate Change, or IPCC, and then going to more national for the US, NASA, and then JPL. So the IPCC is a United Nations body, and its charter is to study the science of climate change. This particular organization was awarded the Nobel Prize, the Peace Nobel Prize in 2007, alongside Vice President Al Gore. The IPCC issues assessment reports approximately every 6 years. The latest one was in 2023. And so I really recommend people, if they're interested in, there's different sorts of reports. There are different kinds. There are summaries, which are still rather lengthy. Everything you need to know, I think, is there. It's a very, very good source. I recommend it. Then there's the National Aeronautics and Space Administration, known as NASA. So NASA explores the air and space, but it's known for sending rockets into space and exploring the solar system. But it's also interested in our planet, Earth. And so you can go to this website and see what NASA does in climate science. And finally, to a more local, that is for me here, the Jet Propulsion Laboratory. It's NASA laboratory. It's owned and sponsored by NASA and administered by Caltech. And JPL sends robots and rovers to Mars, but also builds an instrument for remote sensing of the Earth. And this website is also a good source of information. So the first slide is really the most important for all, everyone included, I think, in the next few years. And it says, the message is at the top, that human activities are responsible for global warming. So this is extracted from the latest assessment report. So if you look at the bottom, you see the greenhouse gas concentration from the mid-19th century to today, and you see the drastic increase. And concomitantly, the figure at the top shows an increase in average temperature observed. So this is the global surface temperature increase that increased by 1.1 degree by 2011 to 2020 compared to the 19th century. So this is the assessment, and I'm particularly interested in this topic and see what we can do about it. So this second slide is the same information but split between the past and the future. So to assess the past, we have two means. One is observation. We can just measure temperature, and there are different ways of doing that. And we can also simulate using numerical computer simulations. For the future, however, we only have computer simulation. So it is paramount that we improve simulation and reduce uncertainty so that we are better able to predict the future. The different color coding, if you see at the bottom, SSP stands for Shared Socio-Economic Pathway, and the second digit indicates the radiative forcing in watts per square meter. So as you go into the red, there's more forcing, so it's getting hotter. There are many more metrics to gauge what global warming is doing, and I just indicated temperature, but if you're interested, the IPCC reports are there for you to document. So as I said, to assess the future, it will be done mostly through numerical modeling. The idea itself of the effect of greenhouse gases is pretty old and dates from the late 19th century, when Arrhenius devised a simple mathematical model to calculate the effect of doubling atmospheric carbon dioxide. And later, in the early 20th century, Bianches, formulated the Navier-Stokes equation of fluid dynamic for motion of the atmosphere. And a little later on in the 20s, Richardson developed a system for numerical weather prediction based on these equations. Something that's not indicated here is a little bit after, let's say, late 40s to 50s, then there was the advent of computers as we know it, and it was a slow process. So I fast forward to the 60s, where we can really trace back the ancestor of the current general circulation models, or GCM, in particular, the contribution of Hsu, Kuro, Manabe. And at the bottom, there's a little bit of a disconnect here. I saw it was very interesting to me that the Nobel Prize in Physics in 2021 was awarded to researchers doing very different physics. And it was awarded because they found hidden patterns in the climate and in other complex phenomena. So Manabe and Hasselmann were awarded the Nobel Prize for their pioneering work on developing climate models. And Giorgio Parisi, which might be familiar to people in this audience, for a theoretical solution for a vast array of problems in the theory of complex systems. So for people in this audience, maybe they are familiar with the notion of replica introduced, and that is used in quantum Monte Carlo simulation, for instance. So this is very striking, this particular association of work, which is to a much lesser extent what I'm going to talk about today. So up to now, there was an introduction of really the time dimension, what is weather and climate, and what we're looking between past and future. There's also the notion of space. So to simulate, we use global circulation model for large simulation from the size of the Earth to down to 100 kilometers. But because the computation is so large, it is computationally very expensive. They use the biggest supercomputer that we have on Earth. So below this resolution, the physical processes must be represented by something simpler that capture the average, so to say, of what's happening. And the method to do that is called parameterization. So parameterization is a set of semi-empirical formulae and that capture what's happening below this resolution. There are other models like large eddy simulation that allow to simulate a cloud or two from a few tens of kilometers down to 100 meters. But then we have the same problem. Below a certain resolution, we must represent the subgrid with simplified formulation. So what I'm going to talk about today is a candidate for this parameterization. Oops, maybe too quick. So the basis of the work we have done here at JPL was a theoretical article by Khouider and Alex Bihlo in 2019, which proposed a stochastic model for the boundary layer clouds. So this is a particular parameterization of what's happening. On the left, you see a schematic of the different spatial scale. The large scale is represented in green, and in light blue or navy blue are the microscale and cloud coverage. So an open cell, that's the terminology I will use in the reminder, will be white, and a cloudy cell will be blue. And we're going to use an Ising model to represent this subgrid cloud cover. So this is really the basis of this work. On the right is a flow diagram of how this model works. There is a large scale equation. There's an equation that describes the dynamics of water, which is here Q, at the large scale, which is coupled to the low scale, the smaller scale at here in blue, which is represented by an Ising system, and it's two parameters, H and J. And our contribution is to replace some Markov Chain Monte Carlo that Khouider and Bihlo used initially with quantum annealing, get a spin configuration, or for us, a cloud coverage, and do an average of this cloud coverage over macro scale, and so forth. So the next slide goes into more detail of this equation. So the bulk planetary boundary layer equation for the conservation of total water content is indicated in the green rectangle. Q is the water content, so it's the evaporation, the sum of the evaporation, water, and cloud condensate average from the surface to the top of the boundary layer. U is the horizontal wind component. D is the diffusion of horizontal diffusion of moisture. Tau S and tau T are the surface evaporation and top of the cloud turbulent mixing timescales. F is a forcing parameters. Once this equation is solved, we get the water content, which is then used to calculate the linear term that will be used in the Ising models through this linear equation here on the right, if you can see my cursor. Then we have an Ising model, which is at the bottom. So this is, I guess, what people call a cubo formulation, where the binary variable is defined in 0 and 1. This is the opposite convention that D-Wave use in their Python SDK, and also with a restriction that we're only considering nearest neighbor interactions. Once we get a spin configuration, we average over the macro scale, and then calculate these two different time scale and so on. So this is how the model works. Before showing some of our results, we tried to address one of the premise of this work was that the Ising model was able to capture the cloud coverage. So we wanted to check this premise, and this slide addressed some of this. So what we did, we downloaded remote sensing data, so taken from a satellite, and there are two different sources. For the water content, it's from ERA, which is an acronym within an acronym, ECMWF, so European entity, reanalysis data, which is a particular blend of observation and modeling from the past. So this is in the observation quadrant. This is the left figure. On the right, it's a cloud mask taken by the MODIS instrument, or moderate resolution imager spectral radiometer. Basically, this is a picture taken from a satellite, and where there is a cloud, there's a yellow pixel, and where it's clear, it's a deep blue. So what we did on the right, we use a different resolution of the water content. You put it in the Ising model and see what it was doing. But also here we have 10 by 10 microscopic cells, which will explain some of the features we see and the one we don't see. So what we do see is that basically we're trying to do an inversion by hand, so to say, which one of these figures is closer to what we see with MODIS. And not so surprisingly, we see that the one with the highest resolution for water does a better job. The fact that we cannot do even better doing by hand, although we did it using an inversion method and a Boltzmann machine, it's because here we used a constant for the coupling, the Ising coupling constant. So this is the piece of resistance of the presentation, so to say. This are result for the stochastic model itself. And I need to mention two features that I haven't mentioned so far, is that in the original work of Khouider and Bihlo of the stochastic model, they used a way to solve the Ising model, which was based on the work of Gillespie in 1975, which is a death-birth process. And there is somewhere inside this method a sampling from the Boltzmann distribution. So that's the first important element. The second one is during the evolution of the large scale, the authors keep memory of the cloud coverage and use it to seed for the next solution. So there is a memory that's needed. And because of this memory feature, I tried to use the reverse quantum annealing from D-Wave, which allows to start from a solution and then reverse anneal and come back to another solution. However, it also gives a ground state solution, so to say, so low-lying excited states. And another feature that I need to say is that in the original work of Khouider and Bihlo, they used a temperature that was relative to the other energy scales, and the problem was hot. So they are not interested in a low temperature solution, which is a little bit of a pity given the fact that the D-wave quantum annealer, that's what it does. That's what's complicated to get. And so the next thing we tried is we tried to simulate a higher temperature by scaling the coefficient with coefficient smaller than 1. And so this method simulates a higher temperature. So the two figures, one on the left and one in the center, represent the time evolution of the coupled model. The blue curve is the one you want to concentrate on, and it's the mean cloud area fraction or cloud fraction. This is calculated by looking at the figure on the right, which is for one particular iteration, and counting the number of yellow pixels and divided by the total number of pixels. So that's one element. So what I did for this evolution is, since I didn't know how one needs to set different scales and be careful when doing that, we use simulated annealing for 198 steps of the simulations. And for 2 steps, we use the quantum annealer for each of the 100 microscopic cells and solve 100 different Ising problems. So the iterations where we use the quantum annealer are indicated with the vertical dash line, red, if you can see it, hopefully. So at iteration 30 and 190. So we used a prescribed equation for the linear term related to water. The coupling was a constant, and we scaled the simulated annealing, the quantum annealer with this 1/3 compared to simulated annealing. And for simulated annealing, we didn't use a full sweep going from high temperature to low, but sampled at one constant temperature. So here is a code snippet where using the Python SDK of D-Wave, where we sample from this particular temperature. So these two, the one on the left and on the right, are for 2 different temperatures. The one in the center is historically the first result I got, and it's a good result, meaning the result from the quantum is indicated by the red dot, and at iteration 30 and 40. And what we see is that the red dot is on top of the blue figure, which means that we get the same result from the quantum annealer that we got, by continuity from the classical simulation. So in order to show something that didn't work, what's happening when there's not a good match between the scaling and what we sample from the quantum annealer, I chose a different temperature and changed the simulated annealing, which literally is a different problem, but it's close enough, and also because poking the quantum annealer costs money, for us, it was easier to change the simulated annealing. And we see that when there's a mismatch or this particular scaling is not set correctly, the point found by the quantum annealer is off the blue curve, and therefore we are not where we need to be. The other curves are the higher statistical moments, second and third. And so we see on the left that there is a spike when we use the quantum annealer, and we want to avoid that. So this result demonstrates that we can use the one in the center, that we can use the quantum annealer if we find a good method to set this particular scalar. So I looked into the literature to see what could help me do that. And I found 4 references. It's not an exhaustive search, probably. The first one was recommended by Andrew King of D-Wave, and it's a work by Jack Raymond et al. And they introduced the concept of local and global temperatures and way to estimate them. The second work by John Nelson et al. Showed a method to adjust the effective temperature by modulating the annealing time and energy scale. So we changed the energy scale, but here I didn't change the annealing time. That's something we yet have to do. Oh, something I didn't say is that to scale the Hamiltonian as we did in the previous slide, I needed to turn off the auto-scale feature of the D-Wave quantum annealer. The third one is a sister publication to 2, and really the emphasis is that they showed that the quantum annealer allowed sampling from a low temperature noisy Gibbs distribution. So that's an interesting insight. And lastly, the fourth was interesting to me because they looked at the influence of higher energy into the statistics and samples getting from the quantum annealer. So this is a summary of the reference number 2 by John Nelson et al. What they did, they scaled for some known problems, a particular Ising problem. They scaled the Hamiltonian, and they look at the difference between the distribution they expected and the distribution that they got from the quantum annealer. And they looked at a particular metric, a distance d, and saw that this distance d expressed a compromise, a trade-off between 2 conflicting objectives. And they found that the optimum was between 0.2 and 0.4 when alpha is large enough to be noise resilient, but small enough to avoid the degeneracy breaking properties of the transverse field. So this method might be interesting for us. However, it would be expensive to do that for every microscopic cells and for every iteration. So maybe that's a good starting point, but hopefully we could do some sort of pre-calibration before a run. The second one is from reference number 4. They also rescaled their Hamiltonian by a factor smaller than 1. And I think what you can see from the main point of this article was that using only sampler from the quantum annealer, which can sample up to 10,000, they calculate the partition function that doesn't go over all the different states. So they look at an example for Ising spin with n. So they have the number of samples, which is about 2 orders of magnitude smaller than what the partition function as summation space should be. And they calculate different statistics. And here it's the first moment, so the average, the magnetization. And the main point is that for a small a, the statistics are closer to the theory. So in conclusion, we have demonstrated the stochastic model for the boundary layer of Khouider and Bihlo, assisted by quantum annealing. We could simulate a higher effective temperature by rescaling the Ising model. And we need to improve this method to scale the Hamiltonian used with the quantum annealer. And thank you very much. If you have questions or comments, you can contact me at this email address. Thank you.
Great, thank you very much, Alex. Round of applause on behalf of the other audience members. And I'll open it up for questions. So if anybody has a question for Alex, either raise your hand on the Zoom tool and or speak up or turn your camera on or whatever. Well, I have a question, I guess. So your Ising model is essentially two-dimensional
Exactly.
on a square lattice,
Yes.
which perhaps is a comparatively easy instance of an Ising model to solve with classical means, modulo some details. I was wondering whether there are interesting problems in climate science which
Oh, yes.
might lend themselves to three-dimensional problems, where
Yes.
there might be a better chance to show some sort of quantum advantage of some kind.
Yes. So I chose my poison when I chose this particular topic. And the proposal writing is an optimization within itself. So this particular stochastic model, so Professor Khouider, who works at the University of Victoria in Canada, has devised several models based on the Ising model. And I chose the two-dimensional one, which is important. So here, this equation of motion, that's why it's for low boundary layer. So the boundary layer is a layer of the atmosphere that's closer to the surface. That's where the winds are influenced by the surface, basically. And it's different from the free atmosphere above. Anyway, so for clouds, that's rather important because then it means we are in this equation, the green one, we're dismissing convection. And convection is somewhat important. So we're looking to introduce that in the next model if we get a chance. But then it will be harder. There's a lot of physics that I didn't talk about. Is we also did the inverse of this problem. So although it's for people who deal with spin and have done this for a long time, I want to make sure we can do the basics before that we can run, we can walk before we run. So we did a quantum Boltzmann machine, and we did a Boltzmann machine to invert the Ising in two dimensions using remote sensing. And we're seeing some very, very interesting features of nature that nobody has seen before. But, before going to 3D, I want to make sure that we understand that. And at this juncture, I think we're really discovering what we can do with the Ising. So the answer is yes. Eventually, there's lots of physics, and in particular, where we're going to look for maybe quantum advantage, we'll look at 3 dimensions. Yes. Thank you.
Thank you. Any additional questions for Alex? Well, I have one more, just from your introductory material. You showed a plot showing the past and the future and comparing models. Yeah, this plot. So my question is as follows. What happens in the past simulated data at about 1991? Suddenly the temperature drops in the model, which is good. What happened then that made the temperature drop, at least in the simulated model?
You know what? I do not know. I do not know. I took this slide from a 2,400 pages report, and
but is this not the solution to all our problems? Is to understand what's going on there, and then
yes, but also you can see that the reference here is scaled to the 0 is around 2000, 2019. So I do not know. I can look into it and give you the answer offline. I will try to look into that, but I don't know.
I don't really know what an El Nino is, but I know they happen sometimes. Maybe that's Maybe that's what that is. I don't know. Yeah, I'd be interested because
I'll look into it, and if I can find, I will keep you posted. That's for sure. Thank you. Which really will teach me to not. But there's so many things that there is to understand here. Yeah, that's a good question. Thank you.
Any final questions for Alex?
Nope. Well,
if not, let's thank Alex again. Thank you very much. Lots of interesting ideas in certainly a new field as far as I'm concerned. Thank you.
Very good.
And I look forward to welcoming people to the next INQA online seminar, which will be next Tuesday at, I think, 8 a.m. UK time. So I look forward to seeing people there. Bye-bye, everyone.
Very good. Thank you very much.
Bye. Thank you.
Bye.